So we've got these three relationships for resistors, capacitors, and inductors that allows us to use kind of Ohm's law in a particular way for capacitors and inductors as well as resistors. And it also opens the way for, through use of imaginary numbers, to look at the way these components introduce phase changes into signals. And that will become very important in a couple of applications down the line. So let's see what effect this has on more interesting circuits than just a single component. So let's start with that simple circuit that we keep coming back to, which is the potential divider. So for a potential divider, we have V out equals V in R2 over R1 plus R2. So V out is the output voltage we'd measure here. Not shown on here, is, of course, is the ground. So we could, this is really the voltage measured across resistor 2. And you'll see that, as we've done lots of times, basically the output voltage is proportional to the ratio of this resistor to the total resistance. So obviously, if we put in what our input voltage is, we put in a sinusoidally oscillating voltage like this, then we're basically going to have the same behavior as we would expect. The output voltage is multiplied by a completely real number, which is V0 times by the potential divider ratio. And then this oscillating part is exactly the same as in the input part. There's no imaginary numbers here, no phase shifts, just an output voltage which is proportional to the input voltage in exactly the way you'd expect for a potential divider. So the input and output voltages are going to be in phase with each other, and they're going to be proportional to each other at all times. Things get a bit different when we put a capacitor in. So I've replaced resistor 2 now. Instead of being a resistor, it's a capacitor. And I'm going to use the potential divider rule in exactly the same way as I did for just resistors. And I can do that because with these reactances, Ohm's law kind of works, and this equation, when we first derived it, was derived using Ohm's law. So all we have to remember here is that XC, the capacitive reactance, is 1 over J omega C. So we're going to substitute that in here, and we're going to kind of clean it up a little bit, and we're going to clean it up by basically multiplying the top and bottom of this fraction by J omega C. So this is going to become a 1, this is going to become a 1, and this is going to be J omega R times C. So this is now my equation for the output voltage, and right away what you can see is that, first of all, it depends on frequency again now. So this output voltage is going to be different depending on our frequency, and it also has a J in here, has a complex number. So when we multiply this complex amplitude by the oscillating part of our input voltage, we're going to get a phase change. So let's see what kind of effect that's going to have. So if I look at the denominator of this fraction out here, this is a pure complex number. We've got 1, which is our real part. Omega R, C are all real numbers, so omega R and C are going to be purely real numbers, and so this is multiplied by the J is the imaginary part of this complex number. So what I'm going to do is I'm going to take that denominator, J omega RC, and I'm going to write it in the exponential form that we always do for complex numbers, or that we can do for complex numbers. So we're going to need an amplitude and a phase. So the amplitude is done by using Pythagoras on the real and imaginary parts, and so we're going to have omega squared R squared C squared plus 1 all square rooted. That's going to be my amplitude. And then my phase angle is going to be the inverse tan, the arctan of omega RC. Now it's actually, of course, it's the inverse tan of the imaginary part divided by the real part. our real part is 1 in this case. So we're going to have A tan omega RC. So our output voltage is now going to look like this. And it's going to have a couple of extra parts to it in comparison with the input voltage. The input voltage just had the V naught, EJ omega t. Now we have a phase change and we have an amplitude. And you can see that the this part, this A, is frequency dependent. So as the frequency changes, the output is going to change, even if the input voltage doesn't change. Even if the amplitude of the input voltage stays the same, if we change its frequency, we're going to have a different amplitude of the output. And we're also going to have a phase change, which also depends on the frequency. But the output voltage is now out of phase with the input voltage. So let's take a look at what the implications of that are. I've written out the output voltage here in two different ways. We've got A and we've got our phi. So let's look at it in some different settings. So first of all, let's look at low frequencies. So at low frequencies, omega is going to be a lot less. I'm going to put a lot less than 1 over RC, which of course means that this part here, the first term in our A, is going to be a lot less than 1. And so essentially A is going to, if this gets small enough, A is going to reduce to being just 1, and we're going to have V0 over 1. So the amplitude will be the same as the input amplitude. But what about the phase? So the phase that we get via the arctan function. So this is what the arctan function looks like. It starts from 0, and then as you increase the angle, or you increase the number in the arctan, this goes up and it approaches pi by 2 asymptotically. So RC, of course, is constant, but omega is changing. If we increase omega, we're going to make this bigger, closer to pi by 2. If we make omega small, we're going to be close to 0. And so ultimately, if we have low frequencies here like this, we're going to have an A, which is approximately equal to 1, and a phase angle that's approximately equal to 0. And so in the low frequency range, V naught over A J omega t minus phi is going to look just like the input voltage. They'll be in phase and they will be the same magnitude. If we increase the frequency a little bit so that now omega equals 1 over RC, you'll see that the 1 here becomes, this part becomes 1. So we have A is the square root of 1 plus 1, or 2, and so our amplitude becomes 1 over root 2. So again, if this is 1, what we have here is a complex number on the bottom of our output voltage, which is 1 plus j, which is a vector at 90 degrees, 45 degrees, or pi by 4. And so if we put in arctan of 1, arctan of 1 is around here, it comes in at pi by 4. So at omega equals 1 over RC, the output voltage is going to be a factor of root 2 less than the input voltage, and it's going to be pi by 4, or an eighth of a cycle out of phase with the input. Now at really high frequencies, as we go to much higher frequencies, we're going to go up towards this pi by 2 limit of the arctan function, and so our phase angle is going to become pi by 2. If we look at the bottom of, or the denominator of our amplitude, if this part of the omega squared r squared c squared becomes really, really big, the 1 doesn't matter so much, and so the square root of all this starts to reduce to omega rc. So in the high frequency regime, we're going to have something that is getting progressively smaller as the frequency increases, because we've got 1 over omega here. So the output voltage is going to get smaller and smaller, and is going to get closer and closer to being pi by 2 out of phase with the input. So let's look at what that really looks like for sort of an oscilloscope trace in a real example. So here we've got resistance of 200 ohms, we've got capacitance of 0.1 microfarads, and here we've got a 1 megahertz frequency. So this is in the very high frequency range, so a million hertz, million cycles per second. The blue line is my input voltage, and the orange line is my output voltage. So this is a really, really big number at the bottom here. And so the output voltage is very, very small because omega is so big down here. Meanwhile, this phi is going to be close to 90 degrees, and you maybe can quite see that basically the peak of the orange occurs just about where the blue is going through the zero. And so they're 90 degrees out of phase with each other. If I lower the frequency a little bit down to 100 kilohertz, so the amplitude of the output is increased a little bit more each time, with the peak actually tracking to lower and lower values. At this particular frequency, 7.96 kilohertz, this is for this pair of resistors and capacitors, this is the frequency at which omega equals 1 over RC. Remember, omega is 2 pi times the frequency. So if you put 200 and 0.1 microfarads in here for RC, and you divide by 2 pi, you'll get a frequency of 7.96-ish kilohertz. So at this particular point, the amplitude of the output is the input voltage divided by root 2. And this phase angle here is going to be 45 degrees. And you can kind of see maybe that the peak of the orange is about halfway between the intercept and the peak of the blue in the time axis. Okay, as we go even lower frequency, so now we have 5 kilohertz, the orange curve is getting closer and closer to the blue curve, and eventually I'm hitting 100 hertz here, so it's still oscillating. But we are more or less following the input voltage. This is such a small number that mostly the 1 is dominating here, and the phi is close to 0. I just want to point out that for these graphs, I have changed the time axis scale for each graph to make sure there are 5 oscillations of the input voltage on each one. Obviously, if you were adjusting a scope like this or adjusting a signal generator, those peaks would be getting closer and closer together as well. But just so we can see the phase difference, I wanted to keep them all with a fixed number of oscillations. So I've changed the time scale on that graph. So we can kind of plot that amplitude change and phase change on a graph. The left-hand graph here is the relative voltage of the input and output, and this is the relative amplitude of the voltage signal for the input and the output. So this is output voltage divided by input voltage, and you can see that it drops off really, really quickly. The frequency is here increasing from 0 up to 100,000 hertz. In that same time, in that same range, the phase drops from 0 degrees down to minus 90 degrees, or close to minus 90 degrees. And now these graphs are plotted with linear scales. So this is the actual ratio. So 1 is that the output and input are the same. 0.5 is that the output is half the voltage of the input. However, these, and the frequency goes from 0 to 100,000 linearly. Now, this isn't the normal way we would plot these, because the way these graphs are drawn, because there are considerable changes, we have those reciprocals there with lots of 1 over frequency, 1 over RC and arctangents, etc. Those values change quite quickly for small changes in frequency, particularly close to the lower end. And so these graphs often don't really show all the detail of what's happening. So we tend to prefer to plot these graphs using logarithmic scales and using a unit called the decibel. I just want to talk quickly about the decibel, introduce the decibel to you. The idea is that the decibel is a method of comparing two signals. And it can compare the amplitudes of signals. It can also contain the power contained in the signals. Now, decibels are used not just in electronics; they're also used in radio waves. They're used in sound, of course. There, you're usually comparing the amplitude of a sound compared to the lowest possible amplitude of the sound that a human could hear. So in this case, if we want to express, if we have these two frequencies or two signals, and one has amplitude VA and one has amplitude VB, and we want to compare those amplitudes as a ratio, we can compare them using decibels. And to convert that ratio, VB over VA, so amplitude of this signal, amplitude of this signal, into a decibel, all we do is we divide the two, VB divided by VA. We take the log to base 10. This is not the log, this is the log to base 10. Then we multiply by 10. If we wanted to do the same with powers rather than with amplitudes, remember the power in an oscillating voltage is proportional to the square of the voltage. Remember V squared over R. And so the power is proportional to the square of the amplitude, so we would ratio the squares. Now, it turns out that all that happens due to the laws of logs, VB squared divided by VA squared, that means there's a squared inside the log. We can actually take that squared outside, and it becomes 20 times log to base 10 of the ratio, the original ratio of amplitudes. So just to give you an example, suppose that VA was 9 volts and VB was 2 volts. We plug those in, we've got 2 over 9 times log to base 10 times 10, we get minus 6.53 decibels. And for the power level between the two, so which is proportional to 2 squared and 9 squared, we would have 2 over 9, this time times 20, so this is twice of this one. First thing to notice is those are negative numbers, so these are, and that makes sense because our denominator here was bigger than our numerator. So when we're comparing a small signal with a larger reference signal, we're going to get a negative number for our decibels. One special decibel level that we'll kind of come back to is the level of minus 3 dB. What's so important about minus 3 dB? Well, if you plug that in, you'll find that if the decibel level is minus 3 decibels, then that corresponds to an amplitude ratio of 1 over root 2. Or a power ratio of 1 over 2, so a half. So minus 3 decibels is the level at which the power in the output signal is half what it was in the input signal. So it's a useful reference. And we've already seen that for this circuit, when omega equaled 1 over RC, the output voltage was 1 over root 2 times the input voltage. So the 3 decibel, minus 3 decibel level occurs at this particular point. So if we plot that on a log graph now, we get what's called a Bode plot. And the idea of a Bode plot is you're showing gain and phase together. We'll make some more Bode plots as we go along. We're plotting the gain, what we call the gain, so the decibel logarithmic ratio of the two signals. We plot these two things versus log of frequency, we get this very distinct shape. Very little drop off, and then quite a steep drop off here. And that occurs after we've hit this 1 over RC frequency level. So the 3 decibel level is going to be somewhere around here. And it occurs at around the frequency, if you recall, it was 7,000 something, around the frequency where the frequency equaled 1 over RC. Now the corresponding phase at that point is pi by 2 or 45 degrees. And again, we just plot the phase here. This is in degrees. You could plot in radians as well, won't make any difference. So this is in this case, this is a linear scale. In the horizontal, we have a log scale. Okay, so we're going to look at both plots in a bit more detail, but this kind of shows us that what is actually happening here is that for this circuit that we were looking at, low frequency signals are not attenuated. They don't get very much smaller when they come out of this circuit until you get up to quite a high frequency. Likewise, the phase remains the output signal remains fairly in phase, close to 0 phase difference for quite a way, so up to hundreds of hertz, even into the low thousands of hertz. There's not very much attenuation. It's only when you get above that 1 over RC frequency that the output voltage drops really suddenly. So this is what we would call a low pass filter, in that it kind of lets through slowly varying frequencies. Meanwhile, faster varying frequencies, so higher frequencies, tend to get cut off as they go through this signal. We could do the same analysis as we just did with an inductor as well. For an inductor, instead of having a capacitor, we have an inductor. This time we're going to have the difference that your output voltage is XL over R plus XL. XL is J omega L, and then we can do exactly the same as we did before. The difference here now is that our complex denominator is going to have a minus J, so we're going to have an e to the minus J phi. When we do 1 over that, we're going to end up with a positive phase difference on the output. So it's going to be a very similar kind of output. However, it's kind of the opposite way around. When we look at the equations at different frequency ranges. So at low frequencies, sorry, they're all coming in the wrong order. At low frequencies, this time we're going to have so when this frequency is very, very small, this number is going to be very, very big. And so we're going to have more like we had for the high frequency regime for this capacitor. So if omega is very small, this first part of A is very, very big. We can ignore the 1 and we end up with something like this. Again, omega is very, very small, so this is very, very big, so the arctangent will be close to pi by 2. So for low frequencies, we're going to have phase shifted, strongly phase shifted, and an amplitude that gets bigger and bigger as frequency gets bigger. Again, when omega equals R over L this time, our output is going to be proportional to 1 over root 2, and our phase shift is going to be pi by 4. And then at very high frequencies, these are the wrong way around. At high frequencies, the output follows the input. So it's kind of the opposite way around as we would get with capacitors. So this is going to give us what we would call a high pass filter. So it's going to let through high frequencies because at the high frequencies, the output just equals the input. It's going to tend to block lower frequencies because at low frequencies, the V naught, at low frequencies, this the output voltage is going to get smaller and smaller. So it's kind of the opposite way around. So putting an inductor here has the opposite effect of a capacitor. It blocks low frequencies and lets through high frequencies. One way of looking at that is kind of why that is in a more intuitive way is that at low frequencies, the voltage across the inductor will be small because the voltage across the inductor is proportional to di by dt. So at low frequencies, this is very, very small. So this is more or less like a wire. So this is almost as if we've taken our resistor and then we've connected to it here just an ordinary wire. And so if we had a potential divider that was a resistor and then a wire, we would expect this output here to be 0 or to be very low. Okay, so what I would like you to do as a little exercise is we did the situation where I replaced the lower resistor with a capacitor and an inductor. What I'd like you to do this time is to just flip that. So how does the output change if it's a capacitor here and a resistor here rather than the other way around like we just did? And the same with the inductor. What are the behaviors of these two? So use the same analysis as we did for the inductor and the capacitor. So just to go back, like write out the potential dividers. So if we swapped L and R here, we would have R on the top and R plus XL on the bottom. Go through this analysis and see if you can work out what how those devices will behave in the different frequency regimes as we did for the other two. Okay, so I'm going to leave you with that exercise. Sorry for some of the little PowerPoint glitches in there. Okay, we will stop it there.